If I want to solve this equation, negative 3 halves equals negative 2 sevenths u minus 9 fifths, what might I think about doing?
Start by doing the like terms.
Okay, right. So if this were any other kind of equation, let me write a simpler equation over here. Negative 3u equals negative 2u minus 9. So just for comparison, if this were an equation with no fractions in it at all, then our first objective would be to try and, whoops, I'm sorry, I have too many u's here. Our first objective would be to try to get the like terms on the same side of the equation. So here, my pair of like terms that I see are the two constant terms, the negative 3 and the negative 9. So I could get those on the same side of the equation by doing what to both sides? Adding 9 to both sides. And so then on the left-hand side, negative 3 plus 9 is going to give me positive 6. On the right-hand side, I'll have negative 2u. And then what do I need to do from here to get that u by itself? Divide by negative 2, and then we will be done. That's great. So this is the process that back in January we called reversing the order of operations, right? Get that u by itself by first doing all the addition and subtraction that we can do until there's none left on both sides, then all the multiplication and division that we can do until there's none left on both sides. And what remains standing is u and the solution of our equation. So one option for us to solve this trickier equation is just to take the very same approach. What would that look like? What would I want to add to both sides of the equation on the left here to get my process started? Right, I would need to add, not negative 9 fifths, but I would need to add 9 fifths to both sides of this equation, right? Which on the right-hand side would have the nice benefit of getting rid of the negative 9 fifths and leaving me with just negative 2 sevenths u. On the left-hand side, well, guess what? Now on the left-hand side, I have to do a fraction addition problem. This also gives me the opportunity to reinforce, what am I going to do with the negative sign in front of this 3 halves when it comes to doing fraction arithmetic? Joe? Yeah. So anytime you're dealing with a negative fraction, a rational number which has a negative in front of it, the easiest way to tackle that is to give that negative sign to the numerator. Make it negative 3 halves. Don't give it to both numerator and denominator, because if I did, I'd be dividing a negative by a negative, which is going to give me a positive answer, not a negative answer. So if there's a negative fraction, just slide that negative sign upstairs. Okay, but now I would have to find a common denominator for negative 3 halves and 9 fifths. Let me keep that work over here somewhere. Negative 3 over 2 plus 9 fifths. What's a common denominator for these two fractions? 10. In fact, that's also the least common denominator that we can have. So 10 in both cases, and since I multiplied the two denominators, I can use the cross products to get negative 15 here, and 2 times 9 is 18 here. Add those two together. What's negative 15 plus 18? Negative 3, no, positive 3. Yeah, positive 3, because the 18 is bigger, right, than the 15 in absolute value. So I'll get a positive 3 upstairs, I'll get a 10 downstairs. So when all that arithmetic settles, now the left-hand side of my equation is 3 over 10 equals negative 2 sevenths u. That was actually a lot to do just to accomplish the step which over here took us almost no time and thought, right? Okay, but that is what it is. So now what do I do to this equation to get the u by itself? If I'm mimicking what we did over here on the right-hand side, what should I do on the left? Divide by negative 2 sevenths, exactly. By the way, I see a lot of people at this stage in solving an equation, they can do a lot of tricky stuff, but they get to this step and they forget that this is what they need to do. Oftentimes, I'm grading exams and like, this is the last thing that I'll see, and then people move on to the next question because they forget. Same thing as we did on the right-hand side. Just divide whatever u is being multiplied by, right? So we'll divide by negative 2 sevenths. I'm going to rewrite that arithmetic over here. 3/10 divided by negative 2 sevenths. And again, because it's a negative fraction, let me just gift that negative sign into the numerator. So now, how do I divide two fractions? Yeah, multiply by the reciprocal. So I'll flip the 7 and negative 2, and I'll change the change division for multiplication, and then I'll multiply across, because we are multiplying two fractions. 3 times 7, and And so on the left-hand side of the equation, I'm going to get 21 divided by negative 20. On the right-hand side of the equation, I'll get u. Can we rewrite this fraction in a little bit to make it look simpler? I always find it's a little bit ugly to have a negative in the denominator. So let's just pull that negative out to the front, right? It's the same as multiplying the fraction by negative 1 both upstairs and downstairs. I won't kick that fraction out of bed or whatever the saying is, right? I don't mind if you leave it there, but I prefer generally to have the negative sign out of the front. Okay, so this was a pretty heavy lift, right? Because at each stage of our equation solving process, we had fraction arithmetic hitting us in the face. We had to add together two fractions that happen to have different denominators, so that took us some work. And then we had to divide one fraction by another, which takes another kind of work. Right? It works. I mean, this is going to give us the answer, u equals negative 21/20. But as we wrap up today, I want to propose a different approach to this that reduces your exposure to fraction arithmetic. And anytime you can reduce your exposure to fraction arithmetic, it's a good thing, not because fraction arithmetic is bad, but just because it's going to mitigate your exposure to making common errors in fraction arithmetic, which everyone does. So here's the alternative. So what I'd like to solve this in an alternative fashion. Here's an alternative. And in the alternative, what's going to happen is we're going to wipe out all of our fractions in one fell swoop, right at the beginning of the problem. So that what we're going to get is we're going to get an equation which only has whole numbers in it. And then from there, we can go on autopilot, because we remember how to solve equations when there's only whole numbers in them. And again, it reduces the cognitive load. We spend a little bit more energy up front to get rid of our fractions, but then the rest of it becomes easier. So for me, this is how I like to get over that hump, right? So the method works as follows. One of the nice things about rational numbers, fractions, is that if we multiply them by the right thing, they become no longer fractions anymore. For example, if I take a number like negative 3/2, is there a number I can multiply that by to make it no longer a fraction? Let's think about this for a second. If I multiply this fraction by, well, let's make it something that's a whole number. So let's imagine that I'm multiplying it by a whole number. So I'm going to give it that 1 in the denominator. But let's say I multiply this fraction by 2. What's going to happen? Yeah, up here on top, I'm going to get 6, right? Multiplying across. On the bottom, I'm going to get a 2. But then, right, what's going to happen with that 6 and that 2? Really a negative. I'm going to simplify by dividing by that very same 2 in the numerator and denominator. Right? And when the dust all settles, what am I going to be left with? Negative 3/1, which is another name for the whole number, negative 3, the integer, negative 3. Right? So this is great, because now at that stage, all of our fractions, well, our fraction on the left-hand side of this equation is gone. Right? But of course, we can't get away with only doing that to one side of the equation. I would also have to multiply the other side of the equation by 2 as well, right? We can't unbalance an equation by multiplying only one side by something. So I'd really be stuck with also multiplying the right-hand side of this equation by 2/1. And the bad news about that is that when I multiply the right-hand side by 2/1, this fraction is going to become negative 4/7. This one's going to be negative 18/5. Neither of those two reduce to a whole number. But at least the one on the left-hand side did. Right? So we've made a little bit of progress. Maybe we can do a little bit better. Is there a number that not only can kill my 2 in the denominator here, but could also kill my 5?
10.
How about 10? Let's try it, right? So if I instead had multiplied by 10/1 on the left and the right-hand sides. Now, on the left side, I'm going to have 10 times negative 3, that's negative 30. And again, clearing by 2's, that's going to give me the whole number negative 15. On the right-hand side, this 10/1 distributes, by the way, to both of the two terms inside the parentheses. And for my fraction on the right, 9 times 10 and 5 times 1, it's going to give me minus 90/5, which we can reduce by dividing by...
17. Or divided by 5.
Yeah, it's actually better than that, right? So I divide by 5, and I end up with 18. Right. So I'll get minus 18 here. And so then if we multiplied both sides of this equation by 10, then this 3/2 would go away and become negative 15. This negative 9/5 would go away and become negative 18. But negative 2/7 is going to be negative 20 over 7, which doesn't reduce. So how do we do one step better? Is there something that can get rid of all three of the denominators at the same time?
Suppose if we find the common denominator.
If we find the common denominator for all three of these fractions, that will do, right? Any common multiple of 2, 5, and 7 will do. So the 10 gets our 2 and 5 for us, but it misses the 7. So if we need to add the 7 in, what should I multiply by? Since 7 doesn't have anything in common with 10, or really our only option is to go up to 70. Let's try it. Right? On the left-hand side, 70 times 3 is going to be 210. So I'll have negative 210 over 2, which when I do that arithmetic, I get negative 105. Then on the right-hand side, 9 times 70. So this is one of the small drawbacks, which we can get around in ways that we can talk about next time. We do that division, and then we reduce by 5s, and we end up with, oh gosh, negative 126 when I carry out that division. And then negative 2 times 70 will be negative 140 divided by 7. And when I reduce that by dividing it by 7s, I get negative 20. Wait, did I do that right? Something doesn't sit right. Oh, no, I think, yeah, no, we're good. We're good, we're good. So what we get is an equation now that no longer has fractions in it. And we had to expend a little bit of work up front to decide what do I need to multiply both sides by in order to clear all my denominators. That's what we call it. But now that all the denominators are cleared, we have a clear path to solving this equation, the same way that we solved that other equation with only whole numbers in it, which was do all the addition that you can, and then do whatever division you need to get us to our answer. So that's the good news, is that we end up in the same place having cleared the denominators of our fractions up front. And so the fraction arithmetic that we had to do was limited to just multiplying fractions and then reducing them in ways that reduce to whole numbers, which is nice. We didn't have to do any fraction addition. We didn't have to do any fraction division. All the addition and division in our problem-solving process happened at the level of whole numbers over here on the right, which is always nice. So get some practice with the method of clearing denominators. You can read back through this video if you want to. I'm going to post it up into our stream. You have a practice problem in the form of number 6, as well as other problems that you'll get that are of this form in ALEX. Definitely get some practice with this because that really separates those who cruise through that part of the course and those that continue to struggle with fractions.